heads up, please. It's recording. Okay, so two-dimensional problems. I'm just going to do two examples with you. You would have done these in grade 10, and it is basically a review. The light from a rotating offshore beacon can illuminate effectively up to a distance of 250. A point on the shore is 500 meters from the beacon. From this point, the sight line to the beacon makes an angle of 20 degrees with the shoreline. Okay. What length of shoreline to the nearest degree is effectively illuminated by the beacon? This is very much like the homework problem I just took up with you. So here's our shoreline. Okay, we'll call that the shoreline. And there's our beacon, which is basically a light source. We'll call it B, but I'll write beacon there. Now it says here, a point on shore is 500 meters from the beacon, so we'll just say that's 500 meters. From this point, the sight line to the beacon, so that's the sight line to the beacon from this point, makes an angle of 20 degrees with the shoreline. What length of the shoreline to the nearest degree is effectively illuminated by the beacon? So what we could do is first calculate the height of this triangle to make sure the beacon reaches the shoreline. We'll call this shoreline. Okay, we'll call it H. So H equals 500 sine of 20 degrees, right? Because sine of 20 degrees equals opposite over hypotenuse. So if you solve for H, we get that. And that is approximately equal to, let me calculate it, 500 sine of 20, 171 meters. Now, we're okay. We now know that the beacon can illuminate the shoreline. Because it's 250, right? So now we have this situation here, 250. And this situation here, 250. This should say to the nearest, length is in meters. So what length of shoreline to the nearest meter can effectively be illuminated by the beacon? Okay, so I'm going to do some labeling here. I'll call that D, A, C. All right, and yeah. So what we're going to want to calculate is AC. Is that okay? Are we okay so far? Okay. Okay, so why don't we calculate in triangle ADC or DBC in triangle DBC. So focusing on this triangle here so there's no confusion, we can say that sine of C over 500, right? Sine of C over 500 is equal to sine of 20 over 250. So angle C is equal to inverse sine of 500. Is something wrong? It should be DBC. Thank you for pointing that out. I don't know where I got M from, but it should be not DDC. That wouldn't be a triangle. DBC. How's that? Better? Okay, that's good. Sine 20 over 250, and that is approximately equal to 43.1602 degrees. So this is 43.1602. We know we have an isosceles triangle. This is 43.1602. So we can find, that means, right, this is an isosceles triangle. That means we can find this angle B. So now in triangle ABC, we can solve for angle B, right? So if we focus here, now we can solve for angle B. And now once we know angle B, we can get AC. Angle B equals 180 minus 2 times 43.1602, right? Because it's isosceles. And I get 93.6796. This is actually the way I wish I did my homework question, the homework question. It would have been much easier. So now we can find AC over sine of 93.6796 equals 250 over sine of 43.1602. And I'm sorry, there's not much room here. So I get AD AC is approximately equal to 364.7. 364.7 meters is of shoreline is illuminated by the beacon. Don't forget your conclusion, okay? We should have had a let statement, but you can just say let A, B, C, D be as shown in diagram. Okay? So don't forget to put your let statements and your conclusions on the test. Can I explain anything better? Are we good? I don't know why this says problem 3. It's only problem 2. Okay. The angle of elevation of a hot air balloon climbing vertically changes from 25 degrees, goes from 25 degrees at 10 a.m. to 60 degrees at 10:02. So in 2 minutes, it goes 35 degrees. So don't forget 25 degrees goes from there to there, and our 60 degrees goes from there to there, right? So this little guy is 35 degrees. Right in there is 35. 35 plus 25 is 60. Okay, the point of observation of the angle of elevation is situated 300 meters away from takeoff point. So there's our takeoff point and our balloon is going up. What is the upward speed, assumed constant, of the balloon? Give the answer in meters per second and round to 2 decimal places. So we're going to need to find this total distance and divide it by, well, this is 2 minutes, right? It's traveled for 2 minutes. And they want it in meters per second. This is going to be 120 seconds, right? Okay, it's labeled for us, so we won't worry about the labeling process. But can we say that tan of 25 degrees is equal to h1 over 300, right? Tan of 25 degrees is h1 over 300. So we can solve for h1 is approximately 139.89 23. We also know that tan of 60 is equal to h1 plus h2 over 300. So we know h1 plus h2 is equal to 300 tan 60, and that is approximately equal to 5, sorry, no, this entire degree here is 60. This is 35. Okay. Is 519.6152. So, from this point to this point took 120 seconds. So now we can calculate our speed per second. So H2 is going to be 519.6152 minus H1, 139.8923 all over 120. And this is approximately. Give answers in meters per second and round to 2 decimal places. This will be 3.16 per second. The speed of the balloon is about 3.16 meters per second. Can I answer any questions, any concerns?